Okay, so we will continue the discussion from where we left off last time, which was basically a discussion of general concepts in file systems and how operating systems kernels provide support for file systems. So with that background, today we are going to look at the Minix file system in particular and see how Minix can actually enable the implementation of multiple file systems as well. So before I get into Minix, I want to present a concept that is used by many Unix-like operating systems, including Minix, which is called the virtual file system, or the VFS. So a VFS is essentially a layer within the OS kernel that allows you to have different file systems present in the OS, and yet provide an abstraction that allows access to this file system. So as is shown in this figure, the VFS layer, or which is also called the VFS switch, sits above the implementations of different file systems within the kernel. And this picture actually is Linux specific, but the same concepts are going to apply to Minix, as we will see shortly. So you see underneath the VFS layer are different file systems. So there's a ext file system, there's a riser file system, and so on. And the VFS layer is actually sitting on top of these file systems and providing a file system independent abstraction to the rest of the OS and to user processes. So what happens is system calls that are file system specific always come to the VFS layer first. And the VFS layer then examines which file system is responsible for processing that call. And then it is simply going to forward that call to a specific module that implements the file system. So if it is a read on a ext3 file system, the VFS layer is going to then invoke the read or forward that read to the ext3 implementation of read, and so on and so forth. So this mechanism allows us to add new file systems to the OS kernel very easily, because you just have to write that file system to work with the VFS layer, and then everything above the VFS layer is going to be file system agnostic. So the same concepts are actually going to be true in Minix as well, except that unlike this picture where we have a Linux kernel which is monolithic and all of these components reside inside the kernel, we are going to have in Minix these components being separate system processes. Okay? So in Minix we have a server process which is called the VFS process. The VFS process, as the name suggests, is implementing the virtual file server or the virtual file system functionality, in addition to several other functions, but that is by and large what it mainly does. And as shown in the previous slide, it is essentially a user process or a system process that sits between the actual user processes and the file system or file server processes that implement specific file system functionality. So the VFS switch essentially is implemented by the VFS process, and as we will see, each file system in Minix is going to be a separate user process that's going to interact with this VFS process. Now we will see that not only is a file system a separate process, each mounted partition of a file system is also going to be a separate process. So I'm going to talk a little bit about the functionality provided by the VFS layer or the VFS server process in Minix. And you will see today that the slides actually have more content on them as compared to some of the previous classes. This is because all of the classes are recorded going forward, and I wanted the slides to be more informative than just presenting high-level bullets and explaining more of that. So you will see more details on these slides going forward as well. So coming back to VFS, VFS, as I said, provides an abstraction to the other file server processes. It implements a number of data structures and functions, but by and large it is responsible for 2 or 3 different things. The first is it implements a POSIX system call interface that allows user processes to invoke these system calls, and it also supports a few additional libc calls. So you will see here that the 2 classes of system calls that are implemented in the VFS are all the file management system calls, which would include, and there's a long list of them on this slide. So these include file specific ones such as open, close, read, write, directory specific ones that allow you to create directories and whatnot, system calls that allow you to change file attributes like change mod, chown, change directory, and so on, as well as several others that are specific to mounting and unmounting file systems. And VFS process also supports several process management system calls. Remember that there are other processes such as the VM and the PM that also implement a lot of the process specific functionality, but there are a couple of calls that are process specific but also tied closely to the file system, and those calls are actually supported or implemented rather by the VFS process, specifically the select call that allow you to actually deal with the deal with some file IO as well as file descriptors, and file position manipulation calls are implemented by the VFS layer. And the process and the VFS layer also, the VFS server rather, also interacts with the process manager when you have to deal with things like fork and exec and so on, because some of this, when you start a new process, require it to read a new file from disk, and that call is actually handled by the VFS process. The second key set of functions that are implemented here are to track endpoints for device drivers, because the VFS layer is or the VFS server rather, it's also the process where all of the IO functions flow through. So it has to track what kinds of device drivers are present, character device drivers, block device drivers, what their device names are, because if you remember last time I mentioned that, or 2 classes ago I mentioned that all devices also have file names that reside in the /dev directory. So when you are accessing a device through its file name, that call actually has to flow through the VFS process. So the process has to track the endpoints, which are the drivers that are going to be responsible for implementing device specific functions, and can forward the calls to those drivers when they are received. So here in this slide we have a picture that shows us the typical control flow of how an IO request will flow from a user process to a specific file system. What is not shown here are things that are handled at the device driver layer and below. Those functions were described in an earlier lecture. That's still the case. So we are only looking at file system specific layers and processes in this picture. So as is shown, you have a user process that issues a read system call, and that read system call is going to arrive at the VFS process, which in Minix is implementing our VFS functionality or the VFS switch functionality. And in this case, let's say it is a read to a Minix first file system. So it is going to take that read request and then forward it to one of the Minix file server processes. In this picture, you will see that there are 3 different partitions that are mounted. There's a root partition /, there's a /user partition and a /home partition, and each of these could be separate processes sitting within the system, and depending on which partition the read is reading the file from, you will actually forward it to the right process as well. So very quickly, the user process executes a read. The VFS is going to verify that the read is on a valid file and then forwards the request to the file server that is going to handle it. The file server is going to read that data. Remember that in doing so, it has to deal with the block drivers and device drivers and the hard disk and so on, which we have looked at separately. And once you read the data, you're going to copy it back to the user process and reply to the VFS process that it has executed the request. And the VFS process can then subsequently process other operations. Now, shown in this picture is a more detailed version of the simplified picture that I showed earlier. I put this picture only here because one of the labs or the projects is going to require some modifications to the file server and the implementation of a file system. So it's instructive to understand whatever I showed on the previous slide, how it actually is implemented in more detail within Minix. So the processes are the same. It is just that more steps are shown here that implement the higher level description I presented previously. So in this case, rather than doing a read, we have a different system call. So it's called stat. That's going to look at status of files and so on. So you have a user process that executes a small program, that's a snippet of which is shown in this slide, that calls stat on a particular file. Okay. And so that request is going to come to the VFS process. The VFS process is then going to essentially do a lookup to the root partition. The root partition is going to then essentially resolve that request by actually going to the device driver and trying to read the file, or not read the file, read the directory, and so on. And then you will basically eventually get back a request. In this case, the stat is on a file that actually belongs to the /user partition, as you will see in that snippet of code. So the root partition actually needs to the file server process handling the root partition needs to forward that to the /user file server process. So the figure is also illustrating that although you have a single Minix file system on the disk, you have multiple partitions. Each partition is its own independent Minix file system. So / is an independent Minix file system partition, and /user is one. So there's a file server process for each of them. So it's not just one server process for all devices, it's one server process for each partition. So you will see that in this case the request gets forwarded to the /user file server process, and then eventually after it's processed through the device driver, you are going to send back a reply to the VFS process and then eventually to the user process. So multiple system processes are involved in handling the system call, as is typical in most of the calls that are coming to the file system. Okay. So with that control flow background, let's talk about some more details of how the VFS process is implemented. Now, one of the things that is true of the VFS process, which we have not encountered so far, is that it implements threading. It implements threads to handle concurrent I/O requests, because that's a good way to handle concurrency. Now, it's worth noting, and as I've also mentioned previously, Minix has no support for kernel level threads at all. So we have not actually encountered threads so far in any of the other components within Minix, but this is one of the places where threads are used extensively. And because Minix has no support for kernel level threads, VFS threading is actually implemented using a user level threads library, which is called systhread. So systhread is a user level library that was written specifically for system processes. So if you need to write a system process that works with the microkernel, you can actually use this user level threads library, and it will allow you to implement threading functionality. Of course, there are other threads packages that are also available for user processes. This one was written specifically to make the VFS process concurrent. So the way it works is through a standard master-slave process architecture, where there's a main thread that is waiting for requests, and there are a set of, or a pool of worker threads. Whenever the main thread is going to receive a request, it's going to look for an idle worker thread and hand that request to that worker thread. And once the worker thread is finished with that request, it's going to go back to the idle pool again. That's a very standard way by which you write any concurrent or multi-threaded server, and the VFS server also uses the same concepts to implement a multi-threaded worker pool architecture. Now, it's worth noting that in this architecture, if you start with a certain number of worker threads and you get more simultaneous requests than you have worker threads, then you are going to have to wait meaning that once all the worker threads are busy and a new IO request arrives, that request will be queued. Okay. In more sophisticated servers, the size of the worker thread pool itself can be varied dynamically. So, for example, in the Apache web server, you have a dynamic worker pool where the size of the pool actually varies based on the load that you see in the system. But in Minix, you have a much simpler static worker thread pool, which means that if you have more concurrent requests than you have worker threads, then some of those requests will have to wait until a new thread becomes available. So, the VFS server is going to use these worker threads to interact with all the file server processes, and it does so asynchronously. So, while waiting for a reply, a worker thread is blocked. So, it is synchronous on a per thread basis, but in general the whole process is not going to block because you are using, in this case, user level threads. And remember that in user level thread packages, if one thread blocks, all threads are going to block and the entire process blocks. Since we don't want that to happen, each thread has to use asynchronous IO or asynchronous requests, because if you make a blocking call, then all of the other threads get blocked as well. So while waiting for a reply, a thread is going to be waiting, but in an asynchronous fashion, which allows other worker threads to execute. And when you receive a reply from the other file server process, that worker thread can continue execution and eventually finish processing of that request. Now, this picture here, which I'm not going to go into too much detail, shows us the three types of worker threads that a VFS process supports. And they're called a normal thread, which just does normal work. There's a deadlock thread, which actually is a deadlock resolver. If there is a problem, deadlock in the system, that's the one that is going to be used. And then there's a system worker thread that is used by the process manager and to handle notifications from kernels, the microkernel and so on. So the normal threads handle requests that come from user processes. The system threads handle requests that come from other system tasks such as the process manager or the kernel, and the deadlock thread is actually handling deadlocks in the system. Okay. Now, I'm going to also go through a little more detail of where some of the code for the VFS process resides. It is spread across some multiple files, but all of them are in the VFS folder in the server's directory within the Minix source tree. So here are some of the key data structures that are shown on this slide. So there is fproc, there is vmount, there is vnode, there is flip, and there are a couple others on the next slide. So fproc is essentially our process file table. If you remember the concepts I talked about last time, I said there are file tables that are maintained for each process. So in this case, you essentially have the fproc data structure that is implementing that functionality. Okay. vmount essentially tracks all mounted file system within that are currently present within the system, and it will have information like the device major number, minor number, the mount flags, and several other attributes. The vnode data structure, as the name suggests, essentially is going to track all the inodes in your system. Okay, so essentially for every disk file, you are going to have an inode, and all of those are tracked in the vnode table. Okay. The flip or data structure, which is basically the file position table. For every open file, you are going to have an offset that tells you where that file is, where the file pointer is pointing to, and the flip data structure is going to track that for us. Okay. And there are a few others like the lock data structure that allows us to lock certain parts of a file. And as has been noted here, it is basically used in advisory locking at the process level, not within the kernel. The select essentially is used to implement the select call. And then there is essentially a dmap object that is going to be mapping from the device minor number to a device major number, to a specific device driver, so that you can forward the request to the appropriate device driver. Now, I should mention that because the VFS process is concurrent, it has multiple threads, many of these objects will need locking, but the type of locking that is used will vary from object to object based on how threads actually access them. Okay. And at the bottom of the slides are several pointers where some more information about these data structures is available, and the best place of course is to go to the Minix source tree and then look at some of these files to understand these data structures better. Okay. So now let's come to locking. Again, this is the first time we are encountering threading within the kernel. And whenever you have threads, you have a need for synchronization, because if there are multiple threads that access the same object, then you are going to have race conditions and problems with multiple threads trying to overwrite one another. So you need to implement mutual exclusion or locking to avoid these problems. Okay. Now we'll get to how each of these objects implements locking, but what is shown on this slide are higher level design requirements. And we'll see that VFS locking uses a set of design principles that are very similar to ACID properties. If you have taken a course in databases, you would have heard the term ACID properties, which is an acronym that stands for atomicity, consistency, isolation, and durability. And relational databases implement concurrency and locking using ACID semantics. Now, file systems don't use database semantics like ACID properties, but they have their own set of requirements, and the requirements are listed here. I'm just mentioning that some of them have a similar flavor to ACID properties, although I should also say that this is really not providing database like ACID semantics at all. It's a weaker form of guarantees. Okay. So the first is you want consistency on the replicated data, which means that any system call that accesses data structures like that modify things like file sizes. When you write to a file, you might end up making the file bigger, so that requires us to update the file size. So any system call that makes these kinds of changes have to be mutually exclusive within the VFS process. So there has to be some isolation, which means that when system calls are composed of multiple requests, you have to ensure that the result of a system call should not be impacted by what is happening elsewhere. So it should look like this system call executed by itself, and you do not even know that there are other system calls executing. That's called the isolation property, which is similar to how database transactions work. Okay. Integrity of objects essentially says that you should keep objects in a consistent fashion. So since locking is itself a blocking operation, we'll see that integrity of locks requires some extra locking functions, and some of this is non-preemptive. So you want to ensure that you maintain the integrity of all objects in the kernel. You have no deadlock requirements, which seems to be an obvious requirement that we have. Whenever you are threading and you're acquiring all kinds of locks, you want to ensure that you're not going to have any deadlocks. Very easy principle that you can use even in user level code that you write, which is also used here, is to order the operations in terms of how they acquire locks. Okay, so Minix also does the same thing, or the VFS in Minix does the same thing, and it is going to essentially avoid conflicts between locks by keeping an order and acquire locks in that order, which always ensure that there are no cycles. Okay, deadlocks are caused when you have a cycle in how locks are acquired. So we can avoid that by simply enforcing an order. Okay, we don't want any starvation in the system where because of locking, so we need to make sure that all system calls execute efficiently. You must ensure that one request does not block other requests. You must also ensure that read-only operations can be concurrent. And we'll see how some of this is implemented. So within the VFS process, we essentially have three types of locks, which are very similar to read-write locks. Okay, I hope some of you heard the concept of a read-write lock. A typical lock essentially is mutually exclusive, which means any thread that holds a lock blocks all other threads that are trying to acquire the lock. So that's a standard lock, which means that only one thread can hold that lock at any given time. Now, read-write locks generalize that concept a little bit by allowing a bit more concurrency. And what this says in a read-write lock is that multiple threads can acquire the lock in read mode, where they're only reading the object but not modifying that object. But if you're trying to modify the object, you have to acquire the lock in write mode, which means that it now looks like a normal lock where only that thread holds the lock and all other readers as well as writers in the system are blocked from accessing the object. So the Minix and VFS also support a similar concept, and this allows you to have more concurrency during read but safety during write, where only one writer can write to a data structure. So there are actually three types of locks. There's a TTL read, which is a standard read lock that allows multiple readers to read that object. There's a TTL write, which is a write lock that allows only one writer to hold a lock, no readers or writers allowed. And there is something called a TTL read serial, which allows you to hold read locks on multiple parts of the file. So you can hold a lock on only a part of the file rather than the entire file, or a resource rather than the entire resource. So read locks are somewhat similar to write locks in that you can essentially you don't block other concurrent reads, but you can be upgraded to a write lock, and then the thread will block until the last read lock has left, and so on. So think of this as a way to serialize some of the reading when you don't want full concurrency. So again, there is a link at the bottom that has some more information on these locking primitives within the VFS layer, and we'll see that there are other parts of the system, or the Minix system, that also use locking and use the same concept. Okay. Now, earlier I mentioned that to avoid deadlocks, Minix requires that code has to acquire locks in a certain order, and that order is shown here. So you see a set of tasks or data structures here going from fproc to exec, vmount, vnode, flip, and so on, and that's the order in which that's the order that you have to respect. So what that so as an example, thread cannot lock an fproc object if it actually holds a lock on something down that chain, such as a vmount and so on. So you want to only hold one lock at a time, and that if you hold a lower level lock, you cannot actually acquire a higher ordered lock until you release that first. So I think that's the general concept, and if you do that you will not have any cycles, because you're always holding locks in increasing or increasing order. That's shown in this picture, and that basically means you cannot hold a lower ordered lock and get a higher ordered lock to get that may cause a deadlock. So this concept is respected in many parts of the code, which is in things like vmount, vnode, flip, lock, and so on. So all of these code has to respect this order, but there are several other details of what the locking does, what kinds of locks are actually acquired in each of those components that we are going to look at next. Okay. So let's start with the vmount locking. So here we are trying to grab a lock when mounting and unmounting processes. So this locks entire vnodes, and the main goal here is if you're trying to unmount a process when there are still active IO operations, that is unsafe, because there are still reads and writes that are going to files within a partition, and you're trying to unmount an entire file system. So you don't want that to happen, and this is done by using a lock. Okay. And as is shown here, the way you actually do that is when you try to read, you hold a concurrent lock. That's a read lock that's mentioned as TLL_concur. So read operations and are essentially allowed to proceed in a concurrent fashion. When you want to do a write, you are essentially going to use serial, which basically means that you are going to wait for all the readers to finish, and then you are going to be the only one that has the lock, and then you can proceed. And So you can use this to do create and modify, and then exclusive essentially is actually a real write lock where you are going to block everyone else until the read is finished or until that write is finished. Now, if you look at the next data structure, which is vnode or open file locking, again you have similar concepts. When you want to do a read or open the file in read mode, you are going to essentially lock the vnode using a read lock. When you want to do operations such as create, open, destroying vnodes or inodes, you are going to use the serial mode, and when you want to do write access, you are going to hold a write lock. Okay. So by and large, reads use the concurrent or read lock, write use write locks, and when you want to serialize operations, make sure they go one at a time, you use the serialized lock, which looks like a write lock, but it serializes operations. Okay. Now, as far as locking the flip object is concerned, this is the table that stores the file offset for each open file. Okay, so there are two variables in here, which is the flip count or the ref count, which says how many processes have opened that file for reading or writing, and for each of that process you have flip position, which is the offset within the file. Okay, and in this case you are just going to use a mutex lock. So essentially the locking order is going to help us in this case where you basically hold a simple mutex lock, and whenever you have a flip object on a process's file descriptor, you essentially lock the vnode, which implicitly means that the flip object gets locked as well. Okay. And there are several other concepts, data structures. There is essentially the lock data structure itself, and here you need mutual exclusion for grabbing the lock on, because you need a lock on a lock essentially to implement this the lock functionality. So we assume here that our threading model is non-preemptive, which means all accesses to the structures are automatically atomic. So that's how you're going to implement integrity of the lock object. If you're doing a select, then you essentially use one large global mutex, which is a simple solution, no concurrency allowed. And when you're talking about device drivers and so on, again you essentially access them in a non-blocking fashion, so you don't even need a lock in this case. Okay. Now let me say a few words about how crashes are handled by the VFS process. VFS process is also going to play an important role in all kinds of crash recovery. When your device drivers crash, when the file system process crash, then you got to do something, because remember that the VFS process is essentially the process that is routing requests to all of these other processes, which are device drivers, file system processes, and so on. So you have to say, answer the question, what is going to happen if one of these processes crashes, because the user process might still send a request to the VFS server, and then the VFS server will find that there is no process to forward it to. So the way this is done is somehow the VFS process has to track and the health of these processes. Whenever they crash, then you got to see whether you can recover from them. Okay? So now if the device driver itself crashes, then the file system process that is interfacing with the device driver will try first to restart the driver, and if it is not able to do that, then the VFS process will try to restart the driver through a restart mechanism. Okay. Character devices similar process, but in this case it's the VFS process that's going to try to recover or restart these drivers. Okay. So those are device driver crashes. So they're either handled directly by the VFS process or the file system process that's interfacing with the device driver. Now you could also ask what happens if the file server process itself crashes. In this case, first thing is that the VFS server has to do some cleanup, because if the process has crashed, all open files that are accessing data from that file system, etc., are no longer valid. So you are going to kind of mark them invalid, clean them up, and so on. And then all pending requests are also going to have to be terminated. And then you have to try to restart the file server process and try to recover from the crash by making integrity checks and so on. So the VFS process is going to be responsible for doing some of this. And in this context, I also want to remind you of another component that we had talked about a long time ago, which was called the reincarnation server, or the RS process. The goal of the reincarnation server was also to restart processes when they fail. Okay, so the VFS server is playing a role here. The reincarnation server could also have been used to do similar things. Okay. Now I'll move on to talking about the Minix file system itself. Okay. The discussion thus far has focused on the VFS server process, but it is also instructive to understand how the Minix file server process is implemented and how it stores data on disk as part of the Minix file system. Okay. So the interesting thing about the way this is implemented is, first of all, the Minix file system is a completely user level process that works with a partition. It is written as if it's a network server process, which means that it receives messages from, in this case, the VFS server, but those messages could have come from anywhere else as well. Okay, so the other good part is you can make modifications to the file system without having to touch any of the rest of the kernel, okay, which is a nice functionality that we have here. So long as the interface to the VFS layer is not changed, everything else internally can be changed without having to know anything about the rest of Minix. Okay. The other point that the Minix file system designers make is they've written the process in a standalone fashion that you can actually move this to a non-Minix OS as well, because it's written in C. You can compile it, so it just looks like a process that is receiving messages from outside and then reading or writing to partition. So rather than receiving messages from the VFS layer, you could essentially easily turn that into on another system, a process that's receiving messages from some other component, and then implement a user space file system. So it's very easy to use this concept to implement a user space file system. Okay. I mention this because as part of the project, we will be looking at implementing a user space file system as well. And so this gives us a way by which we can implement a process and some data structures that are independent of the OS kernel. Now the picture on this slide shows us the layout of a Minix file system. Okay, so essentially a Minix file system is created on a disk partition. It is going to have all of the information that are needed to store files, and as well as the metadata information such as inode. So as is shown in the picture, if you think of the disk as a sequence of blocks, okay, the first block is going to be the boot block. The second block is going to be a super block. The next few blocks are going to store inodes. Okay, so these are all this is all metadata information. And then all subsequent blocks are going to be data blocks, where you actually store blocks of the file. Okay, that's how the file system is laid out. And in this context, I want to mention that this data structure, or not data structure, this layout rather, is going to work for any type of underlying storage device, whether it's a USB thumb drive, whether it's a floppy disk, which we don't use anymore, of course, or whether it's actually a hard disk or an SSD. The same layout is going to be used. Okay. Now I want to bring back a picture that I had shown you in lecture 5 when we were talking about the boot process. So this is the same picture as the previous slide, but it shows you how that logical sequence of blocks is actually laid out on a disk, a magnetic hard disk, because that's, remember I mentioned last time that you have essentially cylinders and tracks and sectors and so on. So you will see here that the first sector is essentially the master boot record. That is a disk specific block. That's not a file system block. And then that has pointers to partition, then you have essentially partition 1 that is shown here, and that partition 1 is essentially this block. You can have multiple partitions, in which case this array is going to be replicated in each of those disk partitions. So each partition can have its own boot block and super block and so on. Okay. So that's what you want to keep in mind, and you will see that the first block of a partition is the boot block. Excuse me, the first block of the disk is the master boot record. So these are all concepts you want to keep in mind in terms of how blocks are laid out on a disk, how blocks are laid out on a partition and a file system. So let's talk a little bit about each of these entities, the boot block, the super block, the inodes and so on. Okay. Now, if you remember again the discussion from lecture 5, when I was talking about how the OS boots up. Okay. So once you look at the master boot record on the disk, it is going to point you to a boot partition. The boot partition will actually have the first block as the boot block. The boot block is going to have a little small snippet of executable code. Okay. The size of that boot block is 1024 bytes, so it's 2 disk sectors. And when you essentially start booting, you are going to read from that boot block and read those instructions into memory and start executing those instructions. Okay. And more details of how you figure out where the instructions are were actually discussed in lecture 5. So yeah, I would instruct you to go back to that lecture and look at some of the pictures that we had on the lecture slides that give us more details of how the boot process itself works. Okay. So once the system has booted, you are not going to use the boot block anymore. That's only used in the boot process, but the rest of the file system you're still going to use, which includes the super block and the inodes and things of that sort. Okay. Now, not all partitions have to be bootable, but we still assume that the first block is the boot block. If the file system is not a bootable partition, then you will have an entry or a field in that boot block called a magic number that says this is not a bootable partition. So there's no code to load from the boot block. Okay, but the boot block is always present regardless of whether it's a bootable partition, which means it has boot code like the root partition, or it's a non-bootable partition like /user where there is no boot code present. Okay. Now the picture here shows us the super block of the Minix file system. Okay, this is very similar to some of the concepts I was talking about briefly towards the end of the last lecture. Okay. So the super block is essentially a distinguished block in the file system that's always stored at the beginning of the file system. So it appears directly after the boot block. Okay, it has information, important information about the file system itself. Okay. So you will see it has things about inodes and what is the maximum file size and what are the number of zones and things of that sort that are specific to that file system. So when you create the file system, you can actually specify this parameter. By default, the format program for the file system may have some default parameters, but you could say create a file system with 1000 inodes or 500 inodes, and then basically you will do so, and some of that information is going to get recorded in the super block. Okay. Now there are several data structures. I should also mention the super block. So although the super block is stored on disk, when you mount this file system, a copy of the super block is also kept in memory, so that the VFS or rather the MFS or the Minix file system process can use it to access other information. And whenever you modify the super block in memory, it has to be written back to disk as well. Okay. Now, the file system is also going to maintain many data structures in the form of bitmaps that allow us to track things like free inodes and free blocks in the file system and things of that sort. Okay. So the inode bitmap tells us of all the inodes that are kept, which inodes are in use, which means they are actually valid files, and which inodes are empty, which means they can be used to create new files. As far as disk blocks or the data blocks for a files are concerned, they are allocated in terms of 2 to the power n blocks. So you allocate them in chunks of 2 to the power n, and these chunks are referred to as zones in context of Minix. So you basically have multiple zones, and then in each zone you can actually have specific blocks. Okay. Now this zone concept allows us to allocate blocks next to one another when you create a new file. That's merely a heuristic, it's not a requirement. It allows us to not have the blocks of a file spread across the disk, which can increase seek overheads if they were stored on a magnetic disk and so on. Okay. Now to create a file, you first have to get a free inode, and then to allocate data for the file you have to scan the list of blocks and try to find at least one free block, if not a sequence of free block. Okay. And the pointers to some of these data structures are actually there in the supernode. As you, if you go back to the previous slide here, you will see that towards the end there are some entries that point to the inode bitmap and the zone bitmap. Those are the last two entries in the table that's shown in this super block picture. Okay. Now here is a picture of what an inode looks like. The concept is very similar to the multi-level index inode I showed you last time. Okay. So the first few entries of the inode are going to store the user who created the ID of the user who created the file, the group file, and so on. You will essentially have the size of the file, the access time of the file, last modification time, and so on. Okay. And then you have block pointers, which are called zone pointers here. You will see that there are 7 direct pointers referred to as zone 0 through zone 6. Those are direct disk block pointers. They point to blocks that are stored on disk. So if your file has less than 6 or 7 blocks, you are going to access them to direct pointers. If it grows beyond 7, you are going to have an indirect zone pointer that's itself going to point another block where there are multiple pointers. So you have one level of indirection. And then you can also have double indirect, as is shown here. Okay. There's an unused entry that is kept for future use. If you want to support even larger files in the file system, you can use that entry to create a triple indirect, which is also what I had mentioned in the last class. So exactly the same concepts are true here. Okay. Now one interesting thing you have to note here is as far as the inode is concerned, each inode has an ID. Okay. That is the number that is a unique ID for a file. Okay. So essentially from the file system's perspective, files are numbered, and the number of a file is essentially the inode number. Okay. So if you type ls-i on any Unix file system, you will essentially see file names with the inode numbers that are associated with it that tell you internally how does the OS identify files. Okay. File names are the mechanism by which users identify files, but the OS itself or the file system uses numbers that are associated with the file to identify it. Now the interesting thing here that you will see in this picture of an inode is the file name is actually not included in the inode itself. Okay? Because file names are actually kept in the directory structure. So think of a directory as a table where for each file in that directory you have a file name, and that file name points to a number that refers to the inode. So the mapping between names to inode numbers are stored in the directory, and once you have the number that is associated with the file, you look up that specific inode, and then you get this data structure which gives you access to all of the other information in the file. Okay, so the important point I'm making is the name of the file is actually not stored in the inode itself, it's stored in the directory. Okay. Now as far as how to get to a specific inode, because inodes are kept in a known location, you can, and they are of a fixed size, as you will see here, they are 64 bytes in size, you can directly find the location of a specific inode. So going back 2 or 3 pictures, so you will see here in this picture, in the file system layout, the inodes essentially are stored right after the super block, and each block data block on the disk is 1024 bytes. Each inode is 64 bytes, and so you can essentially say find the offset of every inode because they are stored in sequence. In other words, there is no table telling us where inode 17 is stored. You just compute that using a simple equation. It's offset 64 times 17, starting with the beginning of the inode blocks that are shown in this picture. Okay, so that is how once you actually go to a table directory and find the file name and find its file ID or the inode number, you are going to index into these blocks to a specific offset, and you can read that inode from that location. Okay, so there are a few other data structures to keep in mind. Was what the file system block cache, and I mentioned that both when we talked about device drivers as well as very briefly last time. And this is basically an LRU cache, which caches recently read data blocks for a file by the file system. Okay, so the idea is if you are going to repeatedly do I/O on the blocks, you don't have to read it over and over again from the disk. You keep it in the buffer cache, and then you just modify or read from that buffer cache. And then remember also last time I said when you modify a block, it becomes dirty, and dirty blocks can be written to the cache using a write through or a write back mechanism. Most file systems opt for performance over reliability and use write back. So when you write to a block of a file, it's only going to come to the buffer cache and modify the corresponding cached block, and then the write is going to return. At a later time, the block is going to get evicted from the cache and put on disk, or you are going to have a sync operation that writes it to disk, or in many file systems you have periodic background process. When there's no file activity, it's going to write out all the dirty blocks so that they eventually go to disk. Okay, so that's how the block cache is actually implemented. Okay. Now Minix file system looks like any other Unix file system, which means that there are partitions. Each partition has to be mounted using the mount operation before you can actually access that. Okay, so the mount operation essentially takes a partition and attaches it to some part of the file system hierarchy. Okay, so that's what is shown here, saying you have a root file system, and then you have mounted a /user file system, and then you basically mount two more file systems, which basically allows you to extend that file system hierarchy. So from the user's perspective, they don't actually see that different partitions are mounted. It looks like one uniform file system hierarchy starting from / and then you just descend down the hierarchy. And the fact that you're crossing mount point, etc., is only known to the OS, but you don't actually see this unless you know that that's a mount point explicitly. Okay, so as far as the mounting process is concerned, you use the mount system call to do this, and you unmount using the umount system call. There are all kinds of issues that can arise, such as errors when you try to mount and so on, and all of those things are essentially going to be handled by the VFS layer. There is a list of these shown here, but I'm not going to go into the details of this error handling, except to say that they are implemented within the VFS layer, and specifically in many cases the file server process that implements that file system functionality. Okay, so with that I'm going to end the lecture on Minix file system. So just to briefly recap, we talked about two concepts. We talked about the VFS server process and how it uses the VFS switch concept to implement to allow multiple file systems to be implemented. Each file system is also its own server process, or each mounted file system is its own server process. They collaborate with the VFS process to implement file system functionality. And I talked about the Minix file system, that is the key file system that Minix implements, and how that implements some of the file system functionality using a user serve process. Okay. So we'll end that discussion here today, and then next time we'll talk about a new concept within the OS, which is networking.